8-5 day 1 is where we are at. So determinants are still really the focus. Basically, over the next 2 lessons, I'm just going to show you stuff that you can do with them. Basically, three things. And the case we'll really focus on is the 3x3. Some stuff that we can do with that. Though in the second day at 2x2, it'll come up. 3 things total. In this first day, I'm going to show you 2 of them. And we'll dive right into the first. All right, you can use a determinant under kind of a unique situation to get the area of a triangle. Now you might think you don't need matrices to find the area of a triangle. We know how to do that, and that's true. Here's what I want to show you, though, is that the information that we're given, and it certainly doesn't have to be in quadrant 1, but what we're saying is here's what you know about the triangle. You have the x and y coordinates of the points that form the vertices, and that's all you have. You don't have any side lengths, you don't have any base, you don't have any height, you don't have anything like that. Just the locations of the 3 points that form it. Okay? So we could find it without matrices, but it probably would take you a little while to put together all the pieces of how to do it. Not to mention, if you got there, you would see that with what you know how to do, it would basically be, man, it wouldn't be pretty. You'd have to use some trig stuff, like 3 distance formulas, which you could do that 3 times, then do a law of cosines, and then apply it to our area formula from chapter 5. It wouldn't be pretty. Or you can throw all the points in a 3x3 matrix using kind of a column of placeholders, just a column of 1s, do the determinant, and you'd have your area. Now, one other thing before we do an example with this, the thing that the area ends up being half of the determinant. This always freaks people out. Okay, that notation. Area has to be positive. So all that's saying is you could get a determinant that's negative. If that's the case, just multiply it by -1. If the determinant ends up being positive, leave it alone. All right, I'm not even going to plot these points. I mean, you would just see a triangle that's in quadrant 1 as all the coordinates are positive. Doesn't ask us to either. So we just dive right in. Here's point number 1. Point number 2. There's point number 3, and throw in your column of 1s. All right, it's a 3x3, so we stick with our minors. We have 3 of them we need to find. We always take out row 1, and then we'll go and take out some of the other columns. Okay, so when we take out row 1, column 1, we get 2 times 1 minus 3 times 1, which is -1. Taking out column 2, you would get 2 times 1 minus 4 times 1, which would be -2. And then taking out column 3, you would get 2 times 3 minus 4 times 3. And you'd get -2. All right, I'm just going to shorten area to A. Remember, the plus or minus is just there as a reminder that make sure that your answer is positive. So the entry in row 1, column 1 is a 1. And I multiply that by the first minor I found. This works out kind of nice. 0 times technically 2, because remember that second minor, I switched the sign. And then 1 times negative 2. And then it's a bunch of number crunching. Everything in those parentheses simplifies to negative 3. Okay, so here the negative sign comes into play. Take half of it, but then make it positive. And we get 3 over 2, or 1.5 square units. Okay, all the numbers were pretty small, so it ends up being, you know, seems like it would totally depend on the units. Maybe the units are miles, you know, and then it's a huge triangle, but if they were like inches or centimeters, it's a relatively small triangle. All right, only thing I'm going to throw at you here, same process, but I did put some negatives. It's really not going to change anything. I just more or less want to do a second one. I've only got one other thing today to show you. And at some point in class, I don't know if, I mean, I should do it. I don't know if I will, to show you what it would take to find the area of a triangle if we were just given the locations. To do it another way, so you got a good comparison as to how much work this is saving us. I mean, taking this and that a lot of times matrices do that, is they give you another way to do something that can be significantly more efficient in the calculation. This is really where most of the work is we got to go find our 3 minors. Again, the only difference here, negative 2, negative 2. I'm just showing you that, you know, if the, you know, that's a point that's down in quadrant 4 with this method to get the area of that triangle. It doesn't matter if the numbers are negative. Now we've done enough of these. If you want to pause and go through and get all the minors, and I mean, if you felt good about the last one, you could try on this one, go all the way through and see if you can get the correct answer, and then hit play and, you know, see if our work matches. Hopefully it does. That's the one I'm going to eventually switch the sign. Alrighty, looking pretty good. Negative 2 times negative 4 plus negative 2 times negative 6. Nope. Positive 6. That one switches. Plus 1 times negative 2. Looks like we have negative 8 plus, or excuse me, that would be positive 8. Minus 12 would be negative 4. Minus 2 more, so that determinant comes out to be negative 6. But remember, take half of it, and then make sure it's positive. Okay? So it ends up working out with negative numbers as well. Alright, so the last thing I'm going to show you today, this one's kind of interesting. We're just given 2 points, and we're going to come up with the equation of the line that connects them. Kind of like the triangle situation, something we've done before. Okay, we might need to brush up on it a little bit, but you might think, I know how to do that. We would have to use our lines to get a slope, and then plug them back into our equation to get a y-intercept. You can kind of be the judge here if you think this is more work or less. The one thing you're going to see as we do this is sometimes it was a lot of work to get to standard form, and if we wanted the standard form of an equation, specifically a line, this is actually kind of a slick little way to do it. One thing I'm going to point out here that's a little different is, so x1 and y1, x2, y2, those are the points. These are variables. They just stay as x and y. So it's a little bit interesting here that we have variables in our determinant. They're in our matrix that we'll take the determinant of, but that's okay. And it's a part of an equation. We're going to take this determinant and set it equal to 0. So I've already got this one set up. Okay, so we're the simple numbers here. The line that connects the points 2, 4 to negative 3, 1. And like the area ones, I'm not going to graph anything to, you've seen that before. You just plot the 2 points and connect them with a line, and we're going to find the equation of that line. Now, a great place to start is I have some minors that I need to find. Four times 1 minus 3 times 1. 1, 2 would be 2 times 1 minus negative 1 times 1. You always got to be really careful with negative signs when you're doing determinants. And 2 times 3 minus negative 1 times 4. Suppose I kind of forgot to put an answer on there for the second one. Hopefully you did. It's 3. And that's 10. Okay, so this is all going to equal 0. So first up is we take the entry that's in the first row, first column. This is where things get interesting. That's x times 1. But if you think about it, that's good, because right now what's going on is we do this determinant. We're doing it in an equation. Our answer should be an equation. And notice when I add the second one, y times, not 3, but negative 3, we have an equation that has x and y in it. That's what we want. And we have 1 times 10. Now, if you wanted to get standard form, this is pretty slick. X minus, that would be 3y. Let's subtract 10 and put it on the other side. And there we go. That would be standard form. And we've seen this a bunch of times. If you want to get it to slope-intercept, subtract x from both sides. So I'm going to put both answers on here. We'd have negative 3y equals 10 minus x. Divide by negative 3, and we'd get negative 10 thirds plus 1/3 x. And there, of course, is slope-intercept form. And there you have it. Found the equation of a line connecting 2 points with a 3 by 3 determinant.